Welcome! In this session, we'll be exploring the problem number 1042, flower planting with no adjacent. This is an exciting graph-based problem where our goal is to assign flower types to gardens such that no two adjacent gardens share the same type. Let's dive in and uncover the solution step by step. This problem involves planting flowers in a set of gardens. You are given n gardens, each labeled from 1 to n, and you must plant one of 4 types of flowers in each garden. The flower types are represented by the numbers 1, 2, 3, and 4. Additionally, some gardens are connected by paths, which means they are adjacent to one another. The paths are bidirectional, so if garden U is connected to garden V, then garden V is also connected to garden U. Your task is to assign a flower type to each garden in such a way that no two adjacent gardens share the same flower type. If there are multiple valid ways to do this, you can return any one of them. The problem guarantees that at least one solution will always exist. The input includes an integer n, representing the number of gardens, and a list of paths, where each pair, u, v, indicates a connection between two gardens. The output should be a list of integers, with each integer representing the flower type for a specific garden. Let's look at an example to understand the problem better. Suppose there are 3 gardens and the paths are given as 1, 2, 2, 3, 3, 1. In this case, garden 1 is adjacent to gardens 2 and 3, garden 2 is adjacent to gardens 1 and 3, and garden 3 is adjacent to gardens 1 and 2. To ensure that no two adjacent gardens share the same flower type, we could assign flower type 1 to garden 1, flower type 2 to garden 2, and flower type 3 to garden 3. This results in the solution 1, 2, 3. This assignment satisfies the condition since no two connected gardens have the same flower type. Here's another example to illustrate the problem. Suppose there are 4 gardens with paths given as 1, 2, 3, 4. Garden 1 is adjacent to garden 2, so they must have different flower types. Similarly, garden 3 is adjacent to garden 4, so they must also have different flower types. One possible solution is 1, 2, 1, 2. In this case, garden 1 has flower type 1 and garden 2 has flower type 2, while garden 3 and garden 4 alternate with the same pattern. This satisfies the condition that no two adjacent gardens share the same flower type. Now let's consider a slightly more complex example. Suppose there are 5 gardens with paths given as 1, 2, 2, 3, 3, 4, 4, 5, 1, 5. In this scenario, garden 1 is adjacent to gardens 2 and 5, so it must have a different flower type than both. Similarly, garden 3 is adjacent to gardens 2 and 4, so it must also have a unique flower type compared to its neighbors. One possible solution is 1, 2, 3, 4, 1. In this assignment, all adjacent gardens have different flower types, and the condition is satisfied. It's worth noting that the constraints of the problem allow up to 10,000 gardens and 20,000 paths, so the solution must be efficient. Additionally, the problem guarantees that no self-loops or duplicate paths exist, and at least one valid solution will always be possible. To tackle this problem, our goal is to assign one of 4 flower types to each garden such that no two adjacent gardens share the same flower type. This setup can be visualized as a graph, where each garden is a node and the paths between gardens represent edges. The task then becomes a graph coloring problem, where we assign colors, or in this case, flower types, to nodes while respecting adjacency constraints. One approach we could consider is brute force. Here, we would generate all possible combinations of flower assignments for the gardens and verify which, if any, satisfy the adjacency rules. While this approach is conceptually simple, it quickly becomes computationally impractical. With 4 possible flower types and n gardens, there are 4 to the power of n possible combinations to evaluate. This exponential growth in complexity makes the brute force approach infeasible, especially as the number of gardens increases. It's clear that we need a more efficient strategy to solve this problem effectively. An alternative and much more practical method is the greedy approach. Instead of testing every possible combination, we handle each garden one at a time, assigning it a flower type based on the types already used by its neighbors. By examining only the local constraints for each garden, we can efficiently assign the smallest available flower type that doesn't conflict with its neighbors. This significantly reduces computational overhead. In terms of complexity, we process each garden once and check its neighbors, which is manageable given that each garden can have at most 3 neighbors due to the problem's constraints. This results in a time complexity of O, n plus e, where n is the number of gardens and e is the number of paths. Importantly, this approach works because we are guaranteed to have enough flower types for all gardens, specifically 4 flower types for a maximum of 3 neighbors per garden. This ensures that the constraints can always be satisfied without the need for backtracking or more complex validation steps. The optimized greedy algorithm is the strategy we've chosen for this problem because it is both efficient and straightforward to implement. This approach leverages the fact that each garden has at most 3 neighbors and that 4 flower types are always sufficient to satisfy the constraints. Here's how it works. First, we represent the gardens and paths as an adjacency list. Then, we create an array to store the flower type assigned to each garden. For each garden, we look at the flower types used by its neighbors using the adjacency list, and we assign the smallest flower type from 1 to 4 that isn't already in use. The time complexity of this algorithm remains O, n plus e, making it highly efficient. While this approach is tailored to the specific constraints of this problem, such as the availability of 4 flower types and the planar graph structure, it provides an elegant and scalable solution. By focusing on local constraints and avoiding the complexities of brute force, this strategy achieves both simplicity and optimality for the problem at hand. To solve the problem of assigning flower types to gardens such that no 2 adjacent gardens share the same flower type, we can think of this as a graph coloring problem. Here, each garden is represented as a node in a graph, and the paths between gardens are the edges connecting these nodes. The task is to assign one of 4 colors, representing the flower types, to each node in a way that no 2 connected nodes have the same color. To start, we need to parse the input. We define n as the total number of gardens and paths as the list of connections between them. From this, we can build an adjacency list to represent the graph. This adjacency list is a space-efficient way to store all the neighbors of each garden, which will be critical for the flower assignment process. Once we have the input, the next step is to construct the graph. For each pair, A, B, in the paths list, we add B to the adjacency list of A and vice versa, since the graph is undirected. With the graph structure ready, we can initialize our data structures. First, we create an array flowers of size n, where each index represents a garden, and we initialize all values to 0, indicating that no flowers have been assigned yet. We also prepare a set of 4 flower types, 1, 2, 3, 4, which represent the available choices. The next phase involves iterating through each garden. For each garden G, we look at its neighbors, using the graph adjacency list, to determine which flower types are already assigned. By subtracting these unavailable flower types from the set of 4 options, we can select the first available flower type and assign it to the current garden. To assign flower types, we use a greedy approach. For every garden, we choose the smallest flower type that does not conflict with its neighbors. This works because the problem guarantees that no garden has more than 3 neighbors, and with 4 flower types to choose from, there will always be at least one valid option. Once all gardens have been visited and assigned a flower type, we return the flowers array, where each index corresponds to a garden, and the value at that index represents the assigned flower type. Looking deeper, this problem can be understood as a simplified graph coloring problem. The constraints ensure that no node has more than 3 neighbors, so a solution is always possible with 4 colors. The greedy algorithm efficiently handles the coloring within these constraints. Using an adjacency list ensures space efficiency, and the overall time complexity of O, n plus m, where n is the number of gardens and m is the number of paths, makes the algorithm scalable even for large inputs. The data structures used in this algorithm are simple yet effective. First, the adjacency list is crucial for representing the graph efficiently. Instead of using an adjacency matrix that consumes O, and superscript 2, space, the adjacency list only stores the necessary connections, saving space for sparse graphs. The flowers array is another key element, as it allows us to keep track of the flower type assigned to each garden and provides constant time access for updates and lookups. Finally, the set of unavailable flower types is used to track the flower types already assigned to a garden's neighbors. By performing set subtraction, we can quickly determine the available options for a given garden, ensuring that the assignment process remains efficient. When solving this problem, it's important to account for edge cases. For instance, if the graph is disconnected, meaning some gardens have no paths connecting them to others, these isolated gardens can be assigned any flower type since they have no neighbors to create conflicts. In the case of a single garden, we can simply assign it any flower type, such as 1. Even under the maximum constraints, where the number of gardens and paths is very large, for example, n equals 10,000, the algorithm remains efficient due to its linear time complexity. Let's consider a concrete example. Suppose there are 4 gardens, and the paths are given as 1, 2, 2, 3, 3, 4, 4, 1. First, we build the graph. The adjacency list would look like this: Garden 1 connects to Gardens 2 and 4, Garden 2 connects to Gardens 1 and 3, Garden 3 connects to Gardens 2 and 4, and Garden 4 connects to Gardens 3 and 1. Now, we proceed to assign flowers. Starting with Garden 1, we can assign flower type 1. Next, for Garden 2, since its neighbor Garden 1 has flower type 1, we assign flower type 2. For Garden 3, its neighbor Garden 2 has flower type 2, so we assign flower type 1. Finally, for Garden 4, its neighbor Garden 3 has flower type 1, so we assign flower type 2. The final output is 1, 2, 1, 2, where each index corresponds to a garden, and the value represents the assigned flower type. This shows how the algorithm ensures that no 2 adjacent gardens share the same flower type while satisfying the problem's constraints efficiently. This Python implementation solves the problem flower planting with no adjacent, LeetCode number 1042. Let's break it down step by step. 1. Graph representation. The problem describes the gardens and paths connecting them as a graph. Each garden is a node, and each path is an edge between 2 nodes. We construct the graph using an adjacency list, stored in a dictionary. For every path, u, v, we add v to the adjacency list of u and u to the adjacency list of v. 2. Initialization. We initialize an array flowers of size n, number of gardens, with all zeros, representing that no garden has been assigned a flower initially. Indices in this array correspond to garden numbers, 1 based. 3. Assigning flowers. We iterate through each garden, from 1 through n. For each garden, we determine the set of flower types that are already used by its adjacent gardens using the used_flowers set. To ensure no 2 adjacent gardens share the same flower type, we select the first flower type, 1 through 4, that is not in used_flowers and assign it to the current garden. This guarantees a valid assignment. 4. Result. After processing all gardens, the flowers array contains the assigned flower types for each garden. 5. Efficiency. The algorithm is efficient, with a time complexity of O, n plus e, where n is the number of gardens and e is the number of paths. This is because we iterate through all gardens and their neighbors once. This implementation handles edge cases such as gardens with no paths, isolated nodes. Gardens connected in a linear or cyclic manner. Large inputs up to the constraints. The use of a greedy approach ensures correctness while maintaining simplicity and efficiency. Here, we begin implementing the solution in Java. First, we import the necessary libraries and define the solution class with the method garden_noadj, which takes the number of gardens, n, and a list of paths connecting them as input. To represent the garden connections, we create an adjacency list using a list of lists. For each garden, we initialize an empty list to hold its neighbors. Then, by iterating over the paths array, we populate this adjacency list. Since the gardens are labeled from 1 to n, we adjust the indices to be 0-based for easier array manipulation later. Next, we define an array called flowers to store the flower type assigned to each garden. Initially, all entries in this array are 0, indicating that no garden has been assigned a flower yet. Moving into the main part of the algorithm, we loop through each garden to assign it a flower type. For each garden, we prepare a Boolean array usedFlowers, which helps track the flower types already used by its neighboring gardens. Then, we traverse the list of neighbors for the current garden, marking the flower types that are already taken by those neighbors in the usedFlowers array. After identifying which flower types are already in use by the neighboring gardens, we assign the first available flower type to the current garden. This is achieved by iterating over flower types 1 through 4, checking the usedFlowers array. As soon as we find a flower type that hasn't been used, we assign it to the current garden by updating the flowers array and break out of the loop. This ensures that each garden gets the smallest possible flower type that complies with the adjacency constraint. Finally, once all gardens have been processed, we return the flowers array, which contains the assigned flower type for each garden. This approach guarantees a valid configuration, as there are at most 4 neighbors for any garden, and we have 4 flower types available. By systematically checking and assigning flower types in this way, we ensure that no 2 adjacent gardens share the same flower type, satisfying the problem's requirements. In this problem, we need to assign a flower type to each garden such that no 2 adjacent gardens have the same flower type. There are 4 flower types available, represented by the numbers 1, 2, 3, and 4. We are given n gardens and a list of paths that define which gardens are adjacent. These paths form an undirected graph, and the task is to produce an array where the ith element represents the flower type assigned to garden I. For example, consider the input with 3 gardens and paths that connect gardens 1 and 2, gardens 2 and 3, and gardens 3 and 1. First, we represent the adjacency information in the form of a graph using an adjacency list. This gives us, garden 1 is adjacent to gardens 2 and 3, garden 2 is adjacent to gardens 1 and 3, and garden 3 is adjacent to gardens 2 and 1. We then initialize an array called flowers with all zeros, where 0 indicates that no flower has been assigned to a garden yet. Now, we begin assigning flowers to the gardens. Starting with garden 1, we see that its adjacent gardens, 2 and 3, have not been assigned any flowers yet. So, we assign flower 1 to garden 1, updating the flowers array to 1, 0, 0. Next, for garden 2, we observe that its adjacent gardens, 1 and 3, have flower 1 already used by garden 1. To ensure no 2 adjacent gardens share a flower, we assign flower 2 to garden 2, which updates the flowers array to 1, 2, 0. Finally, for garden 3, its adjacent gardens, 1 and 2, have used flowers 1 and 2 respectively. Therefore, we assign flower 3 to garden 3, resulting in the final flowers array, 1, 2, 3. This satisfies the condition that no 2 adjacent gardens share the same flower type. The output for this example is 1, 2, 3. In this example, we are given 4 gardens and paths that connect gardens 1 and 2, and gardens 3 and 4. First, we represent the adjacency between gardens using an adjacency list. This gives us, garden 1 is adjacent to garden 2 is adjacent to garden 1, garden 3 is adjacent to garden 4, and garden 4 is adjacent to garden 3. Next, we initialize the flowers array with all zeros, indicating that no flowers have been assigned yet. The array looks like 0, 0, 0, 0 at this stage. We now assign flowers to the gardens. Starting with garden 1, its only adjacent garden, 2, has no flower assigned yet. So, we assign flower 1 to garden 1, updating the flowers array to 1, 0, 0, 0. For garden 2, its adjacent garden, 1, already has flower 1 assigned. To avoid conflict, we assign flower 2 to garden 2, updating the array to 1, 2, 0, 0. Moving to garden 3, its only adjacent garden, 4, has no flower assigned yet. We assign flower 1 to garden 3, resulting in 1, 2, 1, 0. Finally, for garden 4, its adjacent garden, 3, has flower 1 assigned. Thus, we assign flower 2 to garden 4, and the final flowers array becomes 1, 2, 1, 2. This satisfies the condition, and the output for this example is 1, 2, 1, 2. In this example, we have 5 gardens with paths connecting garden 1 to gardens 2, 3, 4, and 5. First, we represent the adjacency relationships using an adjacency list. This gives us, garden 1 is adjacent to gardens 2, 3, 4, and 5, while gardens 2, 3, 4, and 5 are each only adjacent to garden 1. We then initialize the flowers array with all zeros, indicating that no flowers have been assigned yet. At this stage, the array looks like 0, 0, 0, 0, 0. We now assign flowers to the gardens. Starting with garden 1, its adjacent gardens, 2, 3, 4, and 5, have not been assigned any flowers. So, we assign flower 1 to garden 1, updating the flowers array to 1, 0, 0, 0, 0. For garden 2, its adjacent garden, 1, already has flower 1 assigned. To avoid conflict, we assign flower 2 to garden 2, resulting in 1, 2, 0, 0, 0. Similarly, for garden 3, its adjacent garden 1 has flower 1 assigned, so we assign flower 2 to garden 3. The array updates to 1, 2, 2, 0, 0. Following the same logic, we assign flower 2 to garden 4, updating the array to 1, 2, 2, 2, 0, and then to garden 5, resulting in the final flowers array 1, 2, 2, 2, 2. This ensures no two adjacent gardens share the same flower type, and the output for this example is 1, 2, 2, 2, 2. In this algorithm, we aim to assign flower types to each garden such that no two adjacent gardens share the same flower type. To understand the time complexity, we first look at the process of building the adjacency list. This step involves iterating through the paths list, which contains len, paths, edges. Each edge is processed once, so constructing the adjacency list takes O, len, paths, time, which is equivalent to O, e, where e represents the number of edges in the graph. Next, we iterate through the gardens. Since there are n gardens, the loop runs once for each garden. During this iteration, the algorithm collects the flower types used by a garden's neighbors. The total number of neighbor lookups for all gardens is proportional to e because each edge contributes at most 2 neighbors. Thus, this step also has a time complexity of O, e. Now, when assigning a flower type to a garden, the algorithm checks up to 4 flower types to find one that hasn't already been used by its neighbors. Since this is a constant operation, it takes O, 1, for each garden. Repeating this process for all n gardens contributes O, n, to the total time complexity. Combining all the steps, the overall time complexity becomes O, e plus n, where e is the number of edges and n is the number of gardens. For connected graphs, which are either trees or sparse graphs in this problem, e is at most O, n. This means the time complexity simplifies to O, n, in most scenarios. On the space complexity side, the adjacency list uses O, e, space since it stores all edges twice, once for each direction. Additionally, the flowers array, which holds the assigned flower type for each garden, requires O, n, space. Furthermore, the algorithm uses a used_flowers set to temporarily store the flower types used by a garden's neighbors. The size of this set is at most the degree of the garden, and summing up across all gardens gives a total space requirement of O, e, in the worst case. When you combine the adjacency list, the flowers array, and the used_flowers set, the total space complexity is O, e plus n. For sparse graphs, where e is at most O, n, this simplifies to O, n. Thus, the algorithm is both time and space efficient, making it suitable for scenarios with a large number of gardens and edges. To put this into perspective, let's compare this optimized approach to a brute force solution. A naive brute force method would try all possible assignments of flower types to the n gardens, ensuring the constraints are met. Since there are 4 possible flower types for each garden, this method would involve evaluating 4 to the power of n combinations. Checking each combination for validity would add further computational overhead, resulting in an exponential time complexity of O, 4 to the power of n. In contrast, the optimized algorithm avoids this by greedily assigning the first valid flower type for each garden. This drastically reduces the time complexity to O, e plus n. For best-case scenarios, such as when the graph is very sparse, the algorithm runs in O, n, time. In average cases, it still maintains O, n, efficiency. Even in the worst-case scenario, where the graph is dense but constrained to e equals O, n, the time complexity remains O, n, demonstrating its robustness. In conclusion, the optimized algorithm offers a highly efficient solution to the problem. With both time and space complexity of O, n, in most cases, it represents a significant improvement over the brute force approach, which has an exponential time complexity of O, 4 to the power of n. This efficiency makes the algorithm well-suited for handling large input sizes, such as scenarios with up to 10,000 gardens. By leveraging adjacency lists and a greedy strategy, the algorithm ensures that no 2 adjacent gardens share the same flower type while maintaining computational efficiency. Now, let's discuss some common mistakes that can arise when solving this problem. First, using DFS or BFS without pruning invalid assignments can be problematic. If we don't eliminate invalid states as we explore, the algorithm might revisit them repeatedly, leading to inefficiency or even incorrect results. To address this, ensure that once a flower is assigned to a garden, it respects all adjacency constraints. Another frequent error is not accounting for disconnected graphs. Test cases might include multiple disconnected components, and failing to handle these can result in incomplete or incorrect flower assignments. Overcomplicating the algorithm with backtracking is another pitfall. While backtracking is robust, it's unnecessary here because the constraints guarantee that a solution always exists. A simpler greedy approach is sufficient and more efficient. Additionally, assuming all nodes have the same degree can lead to errors. Gardens with more connections require careful attention to adjacent assignments, and this assumption can cause conflicts. Lastly, neglecting edge cases, such as graphs with no paths, a single garden, or maximum constraints, can result in unexpected errors. Always test these scenarios to ensure robustness, especially in competitive settings like interviews. To perform well in interviews, it's important to understand the key insights behind this problem. The most critical observation is that the problem can be solved greedily because there are always more flower types available than the maximum degree of any garden, which is 3. This constraint guarantees that a valid assignment exists. The focus should be on satisfying local constraints. For each garden, simply assign the first flower type that isn't used by its adjacent gardens. This guarantees correctness and simplifies the process. From a complexity standpoint, aim to optimize your solution to O, n plus E, where n is the number of gardens and E is the number of paths. Avoid higher complexity solutions, such as those running in O, n squared, as they are impractical for larger inputs. During interviews, it's crucial to explain why the greedy approach works and how the constraints prevent conflicts naturally. Additionally, this problem is connected to other graph-related challenges, such as LeetCode 886 on possible bipartitions, or LeetCode 785, which asks whether a graph is bipartite. These related problems can help build intuition for solving this kind of graph-based question efficiently. Let's explore some alternative approaches to solving this problem. The optimal method is the greedy approach, where we iterate through each garden and assign the first flower type that doesn't conflict with adjacent gardens. This method is simple, fast, and effective, as it leverages the problem's constraints to avoid unnecessary complexity. However, it doesn't explore all possible assignments, which isn't needed in this case. Another option is backtracking, which involves recursively exploring all possible flower assignments and backtracking whenever conflicts arise. While this guarantees correctness, it's computationally expensive and overkill given the constraints. A third approach is to treat the problem as a graph coloring task, using BFS or DFS to assign flowers during traversal. This method is slightly more structured than greedy but remains efficient, though it requires a bit more implementation effort. Finally, the union find method can be used to pre-process connected components and then assign flowers within each component. This is particularly useful for graphs that are sparse or have many disconnected components, though it adds some pre-processing overhead. Each of these methods has trade-offs, but the greedy approach stands out as the most practical choice for this problem. Thank you for joining me on this problem-solving journey. To summarize, we used a graph coloring approach to solve the flower planting with no adjacent challenge, ensuring no two adjacent gardens shared the same flower type. We explored the importance of adjacency constraints and how greedy algorithms can simplify complex tasks. Don't forget to subscribe for more engaging coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!